very shortly here. And we have our third presenting team from Massachusetts, team flight 01890.
All right, hey, is this thing on? So we are Massachusetts team flight 01890 from Winchester High School. I'm Tom Friedel, this is Scott Check, and this is our project lead and Lord and Master, Jefferson Kim. So today we're going to be pitching to you what we call the Kestrel ER, or the Kestrel Extended Range. So first off, discussing our process of design, we decided we want to focus more than anything else on simplicity. Keep it simple, stupid, that's our motto here. So we started out with what we call the 3 E's: efficiency, effectiveness, and equity. Efficiency would mean how cost-effective the solution is. In this case, meaning keeping crop yield up and keeping costs down. Effectiveness would be how fast and cheap a solution is, which in this case means keeping the max speed up while still keeping costs down. And equity would mean that the solution can be used in many different situations, which in this case means being able to perform the same mission in different environments. The other rules that we kind of focused on were the 8 rules of aircraft design by Barnaby Wayne found. Particularly rule number 1, that there's a surprise in every plane. You need to plan for anything. So our goal in this project is basically just to create a design that follows the 3 E's as closely as we possibly can to sort of maximize the efficiency, the effectiveness, and the equity of our design. And in order to execute this, we emphasize lightness, using light materials and light engine and just light equipment in general. And we wanted to also maximize effectiveness while also still keeping our costs down. So we use cheap yet precise sensors, the X3000 and the X4000. Moving on to our engineering process, we first identified the needs of our design. We needed to fulfill the required operational conditions and concept of operation. So then we had figured that out. We moved on to design, starting with an evolutionary process by going first with the concept design, fleshing things out a little bit more with the preliminary design, and eventually, working everything out with a detailed design. After we've done that, we started getting feedback from our mentor and our coach, trying to work out all the kinks and the bugs in our design, and try to get everything exactly right. Now, next would have been production, but needless to say, we didn't build a drone, so that didn't really happen. Our concept of operations was that the UAV needs to be able to fly above the mission area and detect an infestation within the cornfield. In order to do this, we need to fulfill the required operational conditions, which in this case means a range that is greater than 20 miles, a speed that is greater than 80 knots, and that needs to be maintained in 20 minutes, an absolute ceiling that is greater than 3,000 feet, and it must be able to be launched from our catapult, and it must be able to recover from within a limited space. Now I'm going to turn things over to Scott, who's going to discuss our design process in detail.
So, for our concept design, we knew that we had to maximize the range while minimizing our costs. And one big decision we had to make was if we're going to use multi-engine propulsion or single-engine propulsion. Our single-engine propulsion is most similar to our state design. We have one single engine that must be very powerful, but at the same time is now going to be very heavy and more expensive. We'll also have to deal with engine torque, which is the force that exerts back onto the UAV. Many planes deal with this though, so it should not be too big of an issue. We can also use multi-engine propulsion. For this, we need 2 less powerful engines, but it's also now going to be heavier as we have 2 motors and 2 batteries. And for this, we have 4 designs. We have multi-engine propulsion front-back, which had an engine on the front of the UAV and one on the back. The issue with this though is there's very little room in the fuselage now, and we can't mount the sensors on the wings, as then the wings must be thicker and therefore more expensive. Next, we have multi-engine propulsion standard, which has its engines on the leading edge of the wing. This also, we now have a thicker wing, as our engines are on the wing. There's now going to be more drag as our forward reference area is increased. Next, we have the multi-engine propulsion back wing. The engines of this are on the trailing edge of the wing. And again, our wings must be thicker to accommodate the engines, and there will be an increase in drag. Finally, we have the multi-engine propulsion contra-rotating propeller. This has 2 engines in the front UAV with propellers that spin in opposite directions. These cancel out the engine torque, but it's going to be very loud as the propellers are going to be spinning very closely in opposite directions. It will also be very front-heavy, so it will be not as stable. We analyzed each of our 4 multi-engine designs and came up with this chart, which shows the drag, the maximum velocity, and the stall speed for for a UAV, and we highlight the best choices. From this, we see that an electric motor is going to be best for speed and drag, while gas is the lowest stall speed. None of these numbers, though, are as good as the single engine propulsion. When we look closer at our engine type, we see that gas has absolutely nothing going for it. It's just going to be heavier, it's going to be louder, it's going to pollute, and it's going to have to use oil and gas. And as levels of these go down, the center of gravity of our airplane can change and cause stability issues. On the other hand, an electric motor is just going to be quieter, it's going to be lighter, it's going to be cleaner. So we chose an electric in our design. Coming down to looking at our single engine versus multi-engine, we see that the single engine is going to be better. It's going to be cheaper, it's going to be much, much simpler. It's going to be lighter, and it's going to be less batteries. The multi-engine propulsion, on the other hand, is just going to be more complicated, more expensive, heavier, and loud. The single engine UAV will create a lighter, cheaper UAV. Now, over to Jefferson.
So now we'll proceed to the detail design. First of all, we, unlike the current trend of hovering ability, we do not integrate that in our UAV. First, it's not eco-friendly at all. It creates a lot of noises and it can potentially damage drop right below it by creating an air current towards downwards instead of size or up. So we give up our UAV to give a hovering ability. Fuselage, it has a cross section of hexagonal, deformed hexagonal shape because it is really good for stress and endurance. And we adopted the semi-monocoque design to save a lot of weights there. And in order to fill those holes, we put a carbon fiber skin, which is strong but still light. Lastly, we use the modular design to swap the inner modules so we can increase the range of different applications. And these are the pictures of our fuselage. This is our engine module. It is composed of engine, battery, and outer shell. We choose JM1S engine instead of JM1, and therefore we were able to save $600 and weight about 1 kilogram. And Scott will talk about the wing design.
So for our wing, we decided to design our very own wing from the bottom up. Our airfoil is the NACA 13312, and it is a straight wing. Our wing has a very high camber of 13% of the chord, which allows us to mount at very low incidence of only 2 degrees to the fuselage. Our wing also has an aspect ratio of 6. This allows us to have a really high lift to drag ratio. We also decided to use a straight wing as opposed to a delta wing, as we did in the States. The straight wing can get much more lift in a much smaller area, and it will be much more stable. The delta wing is better for higher speeds, but we decided to go for more stability than higher speeds. So this is our wing in Java foil, which shows basic geometry. This is our airfoil calculated in Java foil, showing lift versus drag, lift versus angle of attack, and other things. And this is a program called NASA's Oil Sim, which allowed us to get a good understanding of about how much lift our wing should be able to get. And finally, we have our wing mounted on our fuselage. Back to Jefferson.
Thank you, Scott. So for our tail and empennage design, we had 3 major candidates. Type A, which is integrated from P-38 during World War II. Type B, which is integrated from the RQ-7 Shadow current U.S. drone. And Type C, this is from the old German missile called Fritz X. We had 3 different criteria to design a tail. First is total control surfaces area, 2, weight, and 3rd is cost. In the table, it clearly shows that Type A has the lowest cost and weight, while having a good enough control surfaces, which is average between Type B and Type C. For our landing gear, our UAV used skid instead of normal wheels because we adopted a concept of short takeoff and landing. So because our landing is very risky and kind of innovative way to land, so we decided to do this. So first, our UAV will approach, and then it will pitch up its nose, kick its rudder to the left, and stall to spin like this. And as it reaches the terminal velocity, the parachute will be deployed right up at the top of the wing, and it will land. So therefore, it is important for us to integrate a shock absorber system that can absorb any shock or impact from the landing. In order to do that, we had 2 candidates, which is spring and foam. Spring was really excellent. It's wicked good, it's efficient. However, it was too expensive and too heavy. Therefore, we used polyethylene foam, And by that, we attach the large foam right under the skid, and that will absorb an entire impact. And these are the pictures of the concept designing of the skid itself. This is our sensor payload. We choose two X3000 and single X4000, and then we hand it to 60 degrees, which gives a total area coverage of 2,400 feet. For our control, for our command, we have autopilot and GPS system to guide UAV to and from mission area. For control, we will be using servos to control actual control surfaces. Lastly, for communication, we gave a UAV a loop over ability by attaching a radio relay system on the weather balloon so we can communicate with the UAV on time even though it's over the horizon. This gives us the ability for our UAV to operate over the horizon or any other interference from the landscape. These are support equipment, which includes a safety pilot box, workstation computer, and ground receivers. These are human resources necessary, including safety pilot, payload operator, and data analyst. Our UAV center of gravity is located along the mid-axis of the wing. Therefore, it's very stable. However, it's slightly off-center in terms of the fuselage center axis because our one side of our wing is actually shorter than the other side in order to compensate the torque. So our Kestrel ER-UAS system has slightly less maximum speed than our old one, the Kestrel UAV. However, it increases range from 10 miles to 100 miles. Therefore, it is more efficient and it's more applicable. Also, our maximum speed can be improved by simply changing the engine module from JM1S to JM1. We have several innovations, but I think these are top three. Modular design, which allow us to have larger range of application to be used. And landing gear strut, this cross-section is actually airfoil, so we design our strut to act like a ventral fin, which gives us more lift. And lastly, the look over ability, which is already explained, to give a autonomous UAV to give its operating parameter even larger than what it used to be. These are our CAD models. So there are 6 steps in our mission: launch, ascend, aerial scan, descend, landing, and data analysis. So before we start our mission, it is important for us to actually analyze what we need to do. So therefore, we have to maximize the objective function by maximizing the detection rate while suppressing the cost and time spent. In order to do that, we adopted a parallel search. It is really good for high-speed flight, like what our UAV is absolutely good for. And the turning will be conducted outside of the mission area to maintain the camera pan. There are 2 major phases in our mission: detection, which UAV will scan the entire area, entire mission area, to come up with some potential spots of infestation. Identification, the UAV will fly over those specific area and double check the presence of the European foreign borders in those spots. So for example mission, it takes, after we finish our setting up, UAV will be launched from the catapult, 60 degrees height, and when it enters the mission area, it will execute its search along the parallel search patterns, which takes about less than an hour and covering total 55 miles. Lastly, it will land it and the data will be delivered to the data analyst. Our UAV is good for multiple purposes. Thanks for the modular design concept. And these are the different examples of what our UAV can do, simply by changing its payload module. So for our maritime system cost, the acquisition cost, which consists of airframe, sensor payload, and support equipment, is total $100,000 approximately. And the calculated objective function is $658,286.16 times hour. Our Kestrel ER is cheaper than AM2, and it is efficient for first 46 mission. We use PVC and carbon fiber, which is light and strong. Electric, because it is eco-friendly, it creates less pollution, it's quieter, and it's more cheaper. the aeronautical design and the hexagonal pillar gave us the ability to minimize the air drag. For conclusion, the team has designed an electric engine unmanned aerial vehicle that can fly over the mission area of total 25 square miles.
The team has learned electric aircraft have potential advantages of high weight-to-thrust ratios, efficiency, flexibility, and high cruise speeds.
And the team has learned that designing aircraft is the art of balancing different design variables. Mission planning is necessary in order to guarantee success.
Thank you.
Thank you very much.
Well, you mentioned about a possibility of frequent occurrence of hard landing.
Yeah.
Would that require that you recalibrate your cameras? I mean, not on something that your aiming or your orientation will change.
So that's why we put both parachute and the shock absorber at the same time, because we did not want to, we definitely don't want to make any impact on our sensor payload, so we maintain that pan without any maintenance required. Or if there's any maintenance, then we can simply change the sensor payload module, because it's like a module, so we can just swap it out. So in any case, if we need to like change it right away, we can just change it. We don't need to like start the maintenance right on the field. So that will save us a lot of time there.
What kind of weight will it sustain? You don't fly parachute, then you need to put wind into consideration, especially on that.
So for the wind, so because our UAV will enter the spin at 1,500 feet above the ground. Even though there is a wind consideration, there will be GPS system guided, so we can use like control surfaces like airfoil, ailerons, rudder, and ailerons to like actually adjust the movement of the UAV by simply changing the direction of the UAV falling. So I believe that we can adjust the falling of the UAV just using the control surfaces.
You mean it's not the pilot who is controlling?
No, there will be no pilot absolutely necessary for this mission.
This type of landing that you chose is fairly unique. Why did you choose this type of landing and what considerations?
So actually, this landing method is not like this one of the dogfighting maneuver that I saw in the History Channel. It was so the pilot said that they will choose that whenever they need to decrease their altitude and speed to chase the low speed enemy. So this is actually conducted by the Hellcat, and this was actually successfully catch the zero right under it. So we thought that this could be integrated by simply slowing down the speed and altitude at the same time, because the potential energy will be directly one-to-one correlation changed to the kinetic energy, right? So therefore, we had to do something to lose that speed for the safe landing. So we choose this method, and then we put parachute to slow down even more at the terminal velocity.
What detection device did you use for the horn?
Our sensor payload will be is an IR, an infrared camera, because this mission will be mostly done in April, late April to early June. Close on the UK, and they will start using the horn, which will start to cause UAV does not require any runways at all because it will be launched from the catapult and we recover from the fall landing. So we do not really think any regulations or restrictions near the airport because our mission area is actually 8.9 miles away from the closest airport. So we thought that there would be no interference from the airport or any traffic from the airport that we need to reach.
So how did you go about using teamwork and what challenges?
So we're all juniors at Winchester High School. We're close friends. So this allowed us to meet very easily during the school day, in between classes at lunch, and after school. We're all part of the robotics team, so we can meet during there. We also utilize social media like email and Facebook and texting to communicate outside school hours. And Google Drive to like share files.
And we live like pretty close to each other, so when there is necessary, we just like meet at some place or we can just meet at school because that's always a possible option. And we had a weekly meeting every Friday because that was also a day for our robotics team, so we took that opportunity to also do this training.
Yeah, typically we sort of, if we had any issues in the design process, it's pretty much as easy as, seeing Jefferson in the hallway, saying, Jefferson, how are we going to get it up this, Scott, can you get this done, so there's something that's there, it's very easy. We had a whole shared document on Google Drive that we were all working on and commenting on, so it's a very centralized process.
Can you say again about how you get to select the form, hexagon, fuselage?
So our fuselage concept was actually integrated from the Taurus cruise missile, which is made from the EADS of Europe. So that actually has like a little bit deformed hexagonal shape, but mostly like the rectangular pillar. But we thought that but we had to give like a little bit of space at the side of our UAV for the like all the batteries and all the avionics to shove it inside of the fuselage itself. So, but if we put it like have a larger rectangle, then that would cause too much like weight to sacrifice. Therefore, we had to like chop down the size, and that's what we came up with the hexagon.
And the weight are not evenly distributed, right?
Yes.
Yeah.
Yes. Our calculation of the weight and balance shows that they were all evenly distributed, and we're trying to put our center of gravity along the center line of the wing, so we can have lift force directly as upwards near the center of gravity as much as possible.
I thought I heard that your wing lengths are not the same.
Yes, they're not same because because of the engine, we are using pretty strong engine, which is like 13.2 kilowatts, I believe. So that actually created a lot of torque. So we had to do something to compensate, or our flight, during our flight time, it would be very not stable at all. So we decided to put shrink a little bit of the one side of the wing instead, and leave the other normal. And then the lift force will help us to actually compensate that force. So that's why we choose to have